So this video is a review of units 1 through 4 for the final exam for 131. I'm skipping unit 5 because I just recorded that video and I'd be just repeating what I just did. If you look back through the course videos right around where we completed these units, you will see essentially the same stuff done in those reviews. So unit 1 was all about functions in function sense. So things you need to know from unit 1. You need to know a definition of a function and all the stuff that goes with that. So what's an input? What's an output? How does that relate to the domain and the range? How you identify those things? What's the notation look like? What are graphs? How do we get graphs? I'll put in parentheses, definitely Desmos does all that work for you. And the idea of modeling, again, Desmos. You've done 1,000 of these project things, so it's y1 tilde stuff with x1 based on whatever type of function it is. We looked at also, say, the stories graph tells. I should say graphs tell. And this was all very general stuff, general definitions. So we didn't look at specific functions per se, just more of inputs, outputs, domain range, all of that stuff. And we did look at various examples. Let me add in here how to tell when a function is increasing. So I'll put in here interval notation was what we used on this. Oops. And how to tell when a function is decreasing over a specific set of intervals. And when is a function constant? Just a real quick example of that. Here's increasing, here's decreasing, here's constant. So you would identify these x values where it ceases from being one of the other things. There's really only two places where things change here, and go from there. We also threw in the idea of a maximum and a minimum, which showed up again when we talked about quadratic functions big time. So then after all of this list of stuff, we looked at all things linear. So then we identified linear functions specifically. They came in the form f of x equals mx plus b. You were to identify the slope as a constant rate of change. You had to find the slope. You could use the formula, say m equals y1 minus, I think we did y2 minus y1 over x2 minus x1. We also identified the y-intercept, which was 0, b, and then you were to interpret these in context, which you will be doing on the final exam, the Desmos portion for sure. Interpret, if I could spell that right. We looked at another version of this line, and that was ax plus by equals c. Not super useful, but we looked at how we could identify the vertical intercept and the horizontal intercept. And those are just the x and y intercepts, respectively. So the vertical intercept occurs at 0, some number for y, I'll label it y1, and the horizontal intercept occurs at some x value, 0. We looked at modeling with linear regression, so we looked at the regression being y1 tilde m x1 plus b using Desmos. Now I need a new page, and we looked at systems of equations, specifically systems of linear equations. And if you recall, we used the matrix calculator. It was a long time ago that helped us set that up, where we had the matrix of coefficients, we use the augmented matrix to solve the system in 2 or 3 variables. And then finally, we looked at piecewise functions. That was everything in Unit 1. So Unit 2 was again more general things. Easy does it. Oh boy, that did not work out. So we looked at the algebra of functions. Such things as addition and subtraction of different things. We started with defining the polynomial function. And then we did addition, subtraction, and multiplication of these functions. We encountered a couple special types of functions, like a binomial function. So multiplying these two together, we use the FOIL method to know how to do that by hand. We included in here scientific notation. So make sure you know how to write that, and you may recall doing this in Desmos, figuring out when does Desmos end up giving you answers in scientific notation. And then we also tossed in here rational exponents. So that connection of, say, x to the m over n equaling the nth root of x to the m, or the nth root of x raised to the m power, those being exactly the same thing. And we also tossed in here properties of exponents. And there were like 8 of them. I'll let you look those up. There was bunches of them, like adding, when do you add the exponents, when do you divide them, and so on and so forth. We also tossed in here composition of functions. So what does this equal, and what does this turn out to be? And we defined the idea of an inverse function. And it just so happened that inverse functions happened when this was true, and when that was true, we called g of x, the notation we used was f inverse of x. And we looked at the graphs of inverse functions and how we switch the domain and range, all that kind of stuff. That was Unit 2. Those first 2 units were, here's all the inverse stuff. Composition of functions, f composition g of x turned out to be something, g composition f of x tended to be something different. When these things were equal exactly to x, not to each other, but to x, which means they do equal each other, then we called it the inverse function. This was just notation, not an exponent. And we noted that we switched the domain and range. So units 3, 4, and 5, we then looked at specific functions. So they met all the definitions of Unit 1 and 2. We could add and subtract them. We could do all kinds of stuff with them. And Unit 3 was one of my favorite units in terms of types, or one of my favorite functions. This is exponential functions. And then logarithmic was the, boy, if I could spell that right. And in exponential functions, we had essentially this one equation ruled it all. And we noted that if b was greater than 1, it looked like this. And if b was less than 1, our graph looked like this. And by less than 1, I mean between 0 and 1. It couldn't be negative, nor could it equal 1. We called this growth, and we called this decay. The domains of both of these was all real numbers. And the ranges of both of these was all values greater than but not equal to 0. And both of them have a horizontal asymptote at y equals 0. We then talked about what was called the growth factor. In this case, it's b. And the decay factor, again over here, it's b. And then the growth rate was the percent growth, and that was equal to, let's see, b was equal to, the rate was equal to b minus 1, where over here the decay rate, r was equal to 1 minus b. That's how we found those two things. And then we looked at a very specific application of these exponential functions. That was the compound interest function. And it was a equals p times 1 plus r over n to the nt. This is for n compounds per year. And it turns out 1 plus r over n to the n was our connection, was our b value for that growth or decay. We then noted with continuous compounds, we got the equation, let's see, the textbook gives it as this, y equals a e to the kt. This is continuously compounded. Of course, you know that e is a number, the irrational number. And here we knew that if k was greater than 0, this was growth, continuous growth. If k was less than 0, this was decay. And the connection to our general exponential equation is that e to the k was equal to b. We then knew that modeling with these things, we would do y1 till the ab to the x1, or y1 till the ab to the kx1. Oops, e to the kx1 if we were using either exponential or linear modeling. And then in Desmos, you had to check log mode if you were using this form in order to get what my math was using. So the calculator, your TI-84 calculator, uses a slightly different function to calculate this than Desmos, and so clicking log mode in Desmos gave you that same function. We then switched to logarithmic functions. And the big connection here is that if we had b to the y was equal to x, that meant log base b of x was equal to y. That was our big connection between the two. And you were to know that they are inverses. That's what made this connection true. You needed to be able to write in either form. You need to be able to evaluate. You need to know that the logarithm spits out an exponent. And you needed to be able to model with these things. And then I'm going to bother to write down the three properties. You also needed to rearrange things with this. So if I had log base b of a times b, that was log base b of a plus log base b of b. If I had log b of a divided by b, that was log b a minus log b b. And if I had log base b of a to the n, that was n times log base b of a. And then we had these two special types of logarithms. Log base 10, we don't write. Let me try again. We need a value in there. Log base 10 of a is really log a. We call that common log. And natural log, well, let me try again. Log base e of a was really natural log, or ln. And those are the things that are programmed into Desmos. And then we solve these things graphically, solve exponential and logarithmic equations graphically and analytically. We mostly did it graphically. And that was Unit 3. Lots going on there, lots of modeling. Oh, I should remind ourselves that if we were modeling with a logarithmic function, this is what we tended to use. That brings us to Unit 4, the last unit. And here was quadratics, and then higher ordered polynomials. So we were introduced to the quadratic function, f of x equals ax squared plus bx plus c, and the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. When the function was in this form, I should say this is only true if we're solving this equation. We learned how to factor quadratics. I suddenly can't spell it. Oh, it's right up there, right? And we did the greatest common factor, and then we did into binomials. We did kind of the A times C method. Remember, it's like this, and this is what's in common between each thing. We also learned in this unit about on the imaginary unit, I equal to the square root of negative 1, and how to work with that. And we learned the zero product property, that if we have A times B equals 0, then we know that A is equal to 0 and or B equals 0. Those are your solutions. And then kind of as a side here, we learned that the X-Intercept, which was written like this, let's say x1 comma 0, was also a solution, was related to the solution. That was x1 equals something. And, that was x equals some value, like the x1, which was the same thing as the root of the equation. So all three of these meant exactly the same thing. We also learned about the vertex and how to find it, and whether it was a max or minimum, and what that told us about, say, a particular function. And we learned the discriminant, b squared minus 4ac, and how that told us the type of solution and how many, real or unreal. And then we jumped into the higher order polynomials, and we started with direct variation of the equations in this form, y equals some k x to the n. This was y varies directly as x to the n power was the language. Kind of like the inverse variation, very similar, except this was multiplication. We learned how to find those, and then we looked at, say, the degree of a polynomial. What does that mean? It's the highest power. We found the X-Intercepts, which are very similar, as I noted before, to the roots, which are similar to the solutions when that polynomial equals 0. And we learned the connection of the graphs. So something that looks like this was y equals x to the n power, where n is even. And it just, this basic shape is what we see the whole time. And then the other one looked like this. Again, y equals x to the n, where n is odd. And there were just variations on that shape. And we learned about maximums and minimums of these. So if I gave a more pronounced graph, say of an odd powered function, we learned that this was a maximum, a local maximum, this was a local minimum. Up here, this was an absolute minimum, the smallest value on the graph. And we talked about how things could increase in between these, just like we did in Unit 2. And by the way, we noted the domain of these for all of them is all real numbers. And then the range for these is everything above the y value of the vertex or below, and for the odd powers, it was all real numbers, always and forever. And finally, we did some regression equations. So y1 tilde x1 squared plus bx1 plus z, or y1 tilde ax1 squared plus, oops, that should be cubed, bx1 squared plus cx1 plus d. And then we discovered that in Desmos you cannot use e because it's already programmed, right, as a number. So if you want to do this, maybe just skip that in the alphabet. A, B, C, D, E, F would be your other value if you're working there. But really, we kind of stuck with these two for modeling. Turns out the R value for all of these is going to get higher and higher. Sorry, the R squared value is going to get closer and closer to 1 the higher power degree you get. The problem is the function you get gets less and less useful the higher you go. So that's a brief overview of all the things we studied in this course. There are, of course, lots more specific details. I encourage you to look through each set of review problems in the textbook, as well as the set of review problems that I attached to the announcement I sent out. And there is a MyMathLab review assignment that you could practice as well to prep for that final exam.